Okay, guys, so before spring break, we had started working on chapter 2, section 2.1, and we actually made it through the first 6 examples. So let's pick up from where we left off, and let's see, that should be right here. Okay, so example 6 was the last thing we had talked about, so we need to pick up from example 7 onward. So here we're looking at basically how we can rewrite our trigonometric expressions in a way that you can use them in calculus. So what we are looking at here is rewriting this expression 1 over 1 plus sine of x such that it is no longer in the fractional form. So basically you want to rewrite it so you don't have a fraction anymore. So you're actually going to start out by using this Pythagorean identity here. So you can see this is cosine square of x equals 1 minus sine square of x, or normally we would write this as sine square of x plus cosine square of x equals 1. So what's happening here is we are actually taking this right-hand side and factoring it using this idea of difference of squares. So a square minus b square equals a plus b, and a minus b is the concept that we are using. So that's why this factors into 1 minus sine of x and 1 plus sine of x. So what's going to happen is if you look at your original expression here, it's 1 over 1 plus sine of x, which is one of these factors that we have here from our Pythagorean identity. So what we do is we take our given expression and we actually multiply it by the conjugate term, which would be the 1 minus sine of x. So we're actually doing that with our numerator and denominator, multiplying both of them by the conjugate term of 1 minus sine of x. So the numerator, when you multiply, you'll end up getting 1 minus sine of x, and denominator, when you multiply, you actually end up getting this expression right here, which is 1 minus sine squared of x. And then using our Pythagorean identity, you can go ahead and rewrite that denominator as cosine square of x, right? And then what we do is we take this cosine square of x and divide it into 1, and take this cosine square of x and divide it into sine of x. So you're actually just separating from step 3 to step 4, where you're separating your numerator, and then each of them will have the denominator of cosine square of x. Now, if you rewrite the 1 over cosine square of x, that becomes your secant squared, again, using the reciprocal identity. And then sine of x over cosine of x will become tangent of x, and 1 over cosine of x will, of course, again become secant of x. So you can see we are rewriting this original expression so that we no longer have fractions. And that's the exact same thing they are asking us to do in our example 7, which is given to us as cosine squared of theta over 1 minus sine of theta. Again, we want to rewrite this without any fraction. So this is the example that's given to us, cosine squared theta minus 1 over sine of theta. So what I'm actually going to do for the first step is use that same Pythagorean identity that we looked at in the example. So that's sine squared of theta plus cosine square of theta equals 1. If I want to get cosine square by itself, I will go ahead and subtract that sine square of theta and move it to the other side. So the first thing I'm going to do is, using this term here, I'm going to substitute my numerator, 1 minus sine squared of theta. Keep your original denominator as it is, okay? Then, talking about those difference of squares that I was looking at in the previous example, a square minus b square can be factored into a plus b and a minus b. So here, where you are given 1 minus sine squared theta, I can actually write that as 1 squared minus sine squared. So that's why a square minus b square. And so when I factor it, it factors into 1 plus sine theta and 1 minus sine theta. So again, using this difference of squares here, I'm going to again rewrite my numerator as 1 plus sine theta, 1 minus sine theta. Keep your original denominator as it is. So now you will notice that I have 1 minus sine theta on the top and I have 1 minus sine theta on the bottom. So they will end up canceling each other out. And then you are finally left behind with 1 plus sine of theta. And this is going to be your answer. So this is us rewriting that original expression of cosine squared theta over 1 minus sine theta without any fractions as 1 plus sine of theta. So just looking at how example 7 was given to you and how this problem number 7 is given, each problem is going to be different. Each approach to solving them is going to be very different. So this here was a very different process, and then our example 7 was a very different process. So you would just have to kind of see what the problem is given to you and then go from there on, depending on which identity you use and how you simplify your expressions, okay? Alrighty. So our next example here is actually asking us to use trigonometric substitution. So they are giving us x equals 2 times tangent theta, and of course your theta is between 0 and pi halves, not including the endpoints, and they're asking us to basically make the substitution right here in square root of 4 plus x squared. So as you will notice that we're taking our x and substituting it with 2 times tangent theta, which is what they gave us initially in the problem. So here, since you have 2 times tangent theta to the second power, you're going to take that second power, apply it to 2. So 2 times 2 gives you the 4. And then tangent with the second power will, of course, become tangent squared theta. Now you will notice that first term has a 4, your second term has a 4. So we take that 4 outside as your greatest common factor. You put 1 as a placeholder for that first term. And then from the second term, you are left behind with the tangent squared theta. So that's going to be left behind. We are again using the Pythagorean identity of 1 plus tangent squared theta equals secant squared theta. So again, you can go back and look at that at the beginning of the chapter. And so making that substitution ends up giving you 4 times secant squared theta. Square root of 4 gives you 2. Square root of secant squared theta gives you 2 times secant of theta. So this ends up becoming your answer after you make the substitution happen with your square root of 4 plus x squared. So we're given a similar sort of example here. We are given x equals 3 times sine of theta, and they're asking us to make this substitution happen in square root of 9 minus x squared. And again, your theta is between 0 and pi halves, not including the endpoint. So let's take a look at how we can solve problem number 8. So let's come back here. We are given square root of 9 minus x squared. The substitution is x equals 3 times sine of theta. So let's take a look at this. So instead of 9 minus x squared, we are going to replace that x with 3 times sine theta, right? So we are given 3 times sine theta to the second power. So remember that second power goes with the 3 and with the sine function. So you end up getting 3 squared times sine squared theta. 3 squared will of course become 9, and then sine squared theta will stay as it is. So we'll bring that answer back into our radical. So now you can replace the second part with 9 times sine squared theta. So now you have square root of 9 minus 9 sine squared theta. Now since both of these terms have a 9 in common, we are going to take that 9 outside as our greatest common factor. For this first term, we're going to put a placeholder of 1, keeping the same sign minus in the middle. We've already taken the 9 outside, so from the second term, we are left behind with sine squared theta, okay? So we will again need to use this same Pythagorean identity. Again, you're moving that sine squared to the other side, and you end up getting cosine squared theta equals 1 minus sine squared theta. So we're going to need to make the substitution happen. So again, in our square root, we have 9. And now we are replacing 1 minus sine squared theta with cosine squared theta. And then you're going to take a square root on each of these expressions. You don't have to write it separately like how I am writing here, but just keep in mind you're going to apply the square root to the 9. So square root of 9 is 3. And then square root of cosine squared. So the square cancels out the square root and you end up getting 3 cosine of theta. Okay, so that's what you should get as your answer once you are done making the substitution and simplifying your expression. So very similar to what you saw happen here in example 8 is the same kind of thing that happens here in problem number 8. Okay, now this last part is actually just to check our answer. So this is going back to example 8 here using this expression of x equals 2 times tangent theta. So the idea is to get tangent theta by itself. If you divide both sides by 2, you end up getting tangent theta equals square x over 2. So you know tangent is opposite over adjacent. So if you use that in a right triangle, and here of course you can see is your angle theta right here. So the opposite side is x, the adjacent side is 2, and then this of course will become your hypotenuse. So use your Pythagorean formula, Pythagorean theorem formula, and use that to find your hypotenuse. And then once you have that, since we got this guy as secant of theta, just basically calculate your secant of theta. Secant, remember, is the reciprocal function for cosine. So cosine is adjacent over hypotenuse, so secant will be hypotenuse over adjacent. So your hypotenuse side is square root of 4 plus x squared. Adjacent side is 2. And if you actually go back to this results that we got here in example 8, you will notice that your answers match. So right now we have secant of theta equals square root of 4 plus x squared over 2. If we multiply both sides by 2, these guys will cancel out. You get square root of 4 plus x squared here. And then of course you will have 2 times secant theta here. And that's the exact same thing that we got when we simplified example 8. So square root of 4 plus x squared equals 2 times secant theta. And we can actually do the same thing for our example 8. So let's go back to our example here. Okay, so we were given x equals, and this is this little statement here, x equals 3 times sine of theta. If I divide both sides by 3, I end up getting sine of theta equals x over 3. And of course, sine is opposite over hypotenuse. So using a little triangle, no, this guy will not work, will it? All right, let's get rid of him. Okay, so let's just do a simple right triangle. If this is our angle theta, this would be opposite, adjacent, and then of course this guy's hypotenuse. So our opposite side is x, our hypotenuse is 3, and we actually need to find the adjacent side. So again, use your, and I'll just call it A for adjacent, to calculate your missing side by using the Pythagorean theorem. So again, I would go ahead and subtract my x squared from both sides since we're trying to find A. And that would be A squared equals 3 squared is 9 minus x squared. And then of course we would take square roots on both sides. Now normally with square roots, we get one positive and negative root. but we know since our triangle has to have a positive value for its side, we're actually going to ignore the negative root and just go with the positive. And you can see our adjacent side is coming out to be square root of 9 minus x squared. So since our solution here is coming out to be cosine of theta, so let's calculate what that cosine value should be. Cosine is adjacent over hypotenuse, right? So our adjacent side, we just calculated square root of 9 minus x squared. Hypotenuse was, of course, 3. So if we try and verify this, that means we would need to multiply both sides by 3. This cancels out here, and you end up getting 3 times cosine of theta equals square root of 9 minus x squared, which is the exact same thing we had. Square root of 9 minus x squared equals 3 times cosine of theta. So you can see our solution ends up checking out correctly. So we are good to go. Okay, so that's the basic right triangle trigonometry. Can also help you check your solution. So we know that the substitution and the simplification we did here was in fact correct. Okay, so that was the last thing that we actually had to talk about here in section 2.1. So let me know if you guys have any questions about this. All right, guys, take care.